In this video I will talk about linear dielectric materials. We saw in the previous example the electric displacement is defined to be epsilon naught times the electric field plus the polarization. Now, because you can use Gauss's law to obtain the electric displacement from symmetry if you know the free charges, the distribution of the free charges, if you want to find the total electric field that is created by all charges, induced dipoles, and the charges that you place in the region, if you want to find E from D, then you have to know the polarization. There are some materials, and in some cases, even for these materials, it is possible to say that the polarization P is equal to epsilon naught times the electric susceptibility times the electric field. Okay, this will be the linear. Okay, this is true if your insulating material is what we call a linear dielectric. Now, there is one subtle thing about this expression. This is polarization, and this is the electric field. This is the total electric field from everything. Here is the issue. You place, let's say we place some free charges. Okay, because that's what you control. You place some free charges, say near some insulator, near some dielectric. Now, these charges will create an electric field. Okay, because we know the electric field exists everywhere around charges. Now, in the area where you have your insulator, you're gonna start having, okay, and I'm thinking about this in terms of time. So this is more like a process as a function of time. You place your charges, they create the electric field, and that electric field will end up polarizing your insulator. Here is the thing. Once you start having induced dipoles inside your dielectric, well, those dipoles are fine dipoles. They are as valid as the charges that you placed at the beginning, and those induced dipoles will affect the total electric field since they are dipoles. And of course, once you change the electric field, that will also affect the polarization, right? And then, if you change the induced dipoles, the polarization, of course, that will affect the total electric field again. And then you keep going on. Of course, there will be a moment in time where this process will stop once you reach equilibrium. But it is important to keep in mind, in these physical processes, it is important to keep in mind what is going on, meaning the physics. And it is important to remember this is the polarization, this is the electric field, and this is valid if your insulating material is a linear dielectric. This is the total electric field, this is your polarization. All right. Now, using the definition for linear dielectrics with the electric displacement, then using this expression for polarization, plug it in here. We take out epsilon naught as a common factor, 1 plus the electric susceptibility times E. This means, okay, what this is telling us is that here for linear dielectrics, D points in the same direction as E, and in fact the electric displacement is proportional to the electric field. Now we call this constant here permittivity, and we use the symbol epsilon, so D would be equal to epsilon times the electric field. And we have one more definition, of course, the relative permittivity. So epsilon, this is what we call permittivity. Now we also define the relative permittivity, which is epsilon over epsilon naught. And by epsilon naught, we call epsilon naught the permittivity of free space, the permittivity of vacuum. This is equal to 1 plus the electric susceptibility. Now, you will often hear about relative permittivity also being called the dielectric constant. And now the reason why this is useful, I mentioned a little bit at the beginning of this video. There are problems where we will know the free charges, the charges we control, not the polarization. We will know those. From those using Gauss's law, we will be able to obtain the electric displacement if there is symmetry. And once you have D, if your dielectric is linear, this helps you go from the electric displacement D to the electric field E, which is everything. If you place an instrument inside your insulator and you measure the delta V, and from that you get, say, the electric field, what you get from your measurements is E. So this approximate relationship in linear dielectrics allows us to go from the charges that we control to the electric field that exists inside the insulator. I can make a figure to illustrate that. So the charges that we control, this will be your, if you want, your thought process or your steps when you're approaching problems inside insulator. You're going to start with the charges that we control. From that, using Gauss, hopefully we will have symmetry. Using Gauss's law for D, you will find the electric displacement. From electric displacement and the fact that it is using the fact that it is a linear dielectric, you will be able to find E, which at the end of the day, this is what affects your potential. If you make a measurement, this is what affects your forces. So when we work in problems, if we want to understand situations and do experiments, what we need to know is E. And linear dielectric materials allow us to go easier from D to E.